What up, YouTube? Today I wanted to review the electronic information section of the ASVAB. So let's get started right away. The first concept I wanted to talk about, or at least review, is Ohm's Law, right? So Ohm's Law, let me write it down here. Ohm's Law. So Ohm's Law just states that voltage is equal to current times resistance. And this equation can be manipulated to get the resistor, the current. So if we wanted to say get the a solve for current, we could just divide the resistance on this side. So we start off from this. It'll be, to get current, we'll just divide both sides of the equation by resistance, and so it'll be the current. Actually, give me a second. It'll be voltage. So it'll be voltage divided by current is equal to voltage divided by resistance is equal to the current. So yep, so this will be it. And then if we wanted to get the resistance, it'll be the same way, where we divide both sides of the equation by current. So in this case, it'll still be voltage divided by current is equal to the resistance. And the way this is done is, for instance, we started with this equation. The voltage is equal to current times resistance. So for instance, the way I got here, like I said, is just divide both sides of the equation by the resistance. And so I divide this side by resistance. I divide the left side of the equal sign by resistance. What happens is, because we have resistance in both the numerator and the denominator, the two resistance here on the right side of the equation cancels, and so now you have I by itself, right? And so if you rewrite this equation here, it becomes voltage divided by resistance or resistor is equal to the current. And that's the similar approach is how we solve for the resistance as well, right? And then the resistor itself can also be broken down further, right? So the resistance can also be looked at. So let's take a closer look at the resistance. So resistance and if you take a closer look, this will be R is equal to divided by the area. And so this is a breakdown of what resistance is made of, right? Where this represents. So if we take, for instance, let's use a sample wire, right? So let's assume that this is a wire, right? The length of this wire from, say, here to here is what this L here represents. And then this area here represents the cross-sectional area, right? So the cross-sectional area is what this A here represents. So if you wanted to solve for the area, you could use a pi r squared to get this area. And then this sign here, or this Greek letter here, represents the resistivity of the material. So that would make up for current. And then in addition to this, let me see how we can move this down a bit. Let's get a new one. Okay. So in addition to this, there's also parallel circuits. We can also talk about parallel circuits. And in parallel circuits, the drawing for a parallel circuit could look something similar to, we could have something similar to this. Actually, give me a second here. So let's use this. This could be our voltage source. And we could have our first resistance here. And then our second resistance here. So we can call this R1, and we could call this R2, right? And I mean, this could be our V. And this would be a representation of a parallel circuit. So parallel circuit, the way we represent this, or at least the way we solve for them, typically would be something similar to this. The equivalent resistance, and then over 1 over R1 plus 1 over R2 and then you can go on and solve for the equivalent resistance. So in this case, to solve for this, one thing we can do, well, to add these two resistance up, we would need to get the same denominator, right? So one way we could do that is, I mean, we could keep the equation, we could keep this resistance, equivalent resistance here, the same, and work on the right side first. And so to get the same denominator for both sides, we will need to multiply this R2 by this side. So it'll look something like this: R2 over R1 times R2. And then the right side of the plus sign would also be R1, or similarly, and then this would have the same denominator, so R1 times R2. And then to solve for the equivalent resistance, we could just, well, another thing, now because they have the same denominator, we don't really need to keep both denominators separately, right? We could have it as, we can rewrite this as R2 plus R1, or R1 plus R2, doesn't really matter. And then we can keep it as the same denominator, right? So to solve for the well, this is still over 1, right? Let's not forget this part. This is still over 1. So to solve for the equivalent resistance, we would just multiply this whole side by R EQ, or equivalent, and then do the same here as well. R EQ. Now we have it in the numerator and the denominator, so these cancel. Let's move the equation this side. So this will be 1 overall. This will look like 1 equal to R2, well, R1 plus R2 divided by R1 times R2. And then now we have the R rec, well, R equivalent, I should say, here, right? So to get R equivalent by itself, we could just divide, this whole expression by itself. And once we do that, we can rewrite this equation as so give me a second here. Let me pull an eraser. Or we can rewrite this whole expression as R equivalent. The RQ is equal to, it'll be 1 divided by the whole thing we had, right? So it'll be R1 plus R2 I'm running out of space here, so bear with me. It'll look something like this. I mean, this can also be, it can be simplified to look something more like this. R equivalent is equal to R1 times R2 divided by R1 plus R2. So this is a simple case that we've solved for R equivalent from the circuit that I drew up there. So now let's talk about, electrical power, right? All the equations that we use to represent power. So power in electrical engineering. Power is represented with a P. Actually, let me be more mindful of space here. So it'll be P is equal to voltage times times current, right? So that's one representation of power. Another representation of power is, and then afterwards I'm going to show you how all these are equal, right? Another one is I squared times R. So I squared times R is also a representation of power. And then the last one that I can think off the top of my head would be V squared divided by R. Now, so let's start off by, let's recall Ohm's law, right? The equation we wrote for Ohm's law was that V was equal to I, or current, times resistance. So let's keep that equation in mind. So let's rewrite this using the Ohm's law. Let's substitute in the I times R for V, right? So it'll be I times R. This is V, right? So I'm going to put parentheses around it, times I, right? Because we've substituted in for the V. So times I. if we multiply this out, now we have what? We have two currents, right? We have two i's, and so it'll be what? I squared times r, right? And we can see that this here, the second equation here, equal to what? The simplification we just had, right? So let's skip that second equation since we've shown equivalence to the first one. Now let's see if the third one also equals to this. So let's substitute in for v, right? So what do we have? We got I times r, right? But it's squared, right? So we'll have to multiply that by itself, and so we'll have another I times r, right? And all is divided by what? The resistance. So now let's try to simplify this. So it looks like we have one I here, or one current here. We have another one here, right? So we'll have I squared, and then we'll also have r squared, right? R squared, and then we got divided by r. But if you look at the equation closely, we see that we got r in the numerator, r squared in the numerator, and then r in the denominator, right? So one of these r's can cancel, right? Can cancel with the r in the denominator. So we will only be left with one r in the numerator. So the equation simplifies to I squared times r, exactly like the two equivalents we've shown, right? So now we see that all the power equations, simplify to the same thing, right? All of it, they're all equal. Even though they may look at face value to be different, they come down to the same, they reduce to the same equivalent. And then we can take a closer look even at current. So for the current, so upon a closer look, we know that current is the amount of charge per unit of time that passes through a specific circuit, right? And we typically represent this with I is equal to the change in Q, which represents Coulomb, divided by change in time, right? And we also know that the unit for current is Ampere, right? So 1 ampere, 1 amp is equal to 1 Coulomb. One Coulomb over a second. And so, yeah. So we can represent current this way as well. And, going back into the Ohm's Law equation. And then there are also circuits, right? There's series circuits, there are parallel circuits. I think I've already drawn what a parallel circuit look like. So a series circuit looks something more like this.
I didn't get that. Could you try again?
That's Siri chiming into my conversation, into our lecture. So a series circuit Look something like this. So if we have a voltage source here, if you have a voltage source here, we can have a resistor here. We can represent this with an R, and then we can represent this with a V. And this is what a series circuit will look like. In addition, we can also represent, this is how we represent like a direct current. So let me show some of the symbols. So DC current or DC direct current. Let me just use the short term here. DC current is represented as this. And AC current, alternating current, is represented like this. And then resistor, as I've just indicated in there, resistor, I'm gonna just write the short version, R, would look something like this. Variable resistor would look similar. And then it'll have this over it. A fuse, so variable resistor, let me put a VR here. A fuse can be represented as this. Capacitor, I'm going to use a C here. Capacitor can be represented as these two. A diode, let me just use a D here. Diode can be represented as, actually give me a second. A diode can be represented as and then lastly, a transistor can be represented as this is supposed to be a triangle. You'll have a circle around it like this. And this can be a C. This can be a B. This can be an E. And this will be a representation of a transistor. Inductors could be, inductors look more like this. And then in addition to this, I mean, something that may also be quite helpful in terms of solving electrical problems would be the metric prefixes, right? So let's talk briefly about metric prefixes here. We know in Ohm's law, it'll be volt per amp. Amperes measure current, and it'll be coulombs. Amps are typically coulombs per second, and volts or voltage Well, let's talk about the metric prefixes here. So typically a nano, let's actually use a table here. This could be like microscopic stuff, right? In very, very small stuff. Let me write like very small stuff here. And then this would be like big. Oh, give me a second. This would be like gigantic numbers. Well, it wouldn't start off gigantic, but it'll make its way to big. Anyways, if I can spell that is. But anyways, so nano typically, would be 10 to the negative 9. It would be represented as 10 to the negative 9. Let me write this here. So this would be nano. So that's nano. And then from nano, we can maybe talk about micro. Micro would be 10 to the negative 6. And then from micro, we can talk about milli. That M didn't come out right, so. And that'll be 10 to the negative 3. And then we can go to centi. Which would be 10 to the negative 2. And then on the right side, now let's talk about the large numbers. So on the right side, we can start off with kilo. Kilo will be 10 to the 3rd. Actually, give me a second. I should have been the other way. So this would be 10 to the 3rd, and this would be kilo. And we can do mega, which would be 10 to the 6. Then we could do giga after mega, so that'll be 10 to the 9th. And these, I'm going to stop here so that, to avoid information overload. I'm going to break these videos into sections. And so, yeah, this will be the general overview of the electronics information section of the ASVAB. Now, if you have questions, concerns, or just any comments, you could just put them in the comment section, and I'm going to do my best to get back to you as soon as possible. If you enjoyed this video, do make sure to subscribe to the channel. I have a few videos in the pipeline, so be on the lookout, and let's have some fun. Thank you.